Up next, we have Tom Ulrich, who comes to us from Idaho National Laboratory. He will be talking to us about a human performance simulator.
Whoops. All right, yeah, thank you very much. So I guess just a little bit of background. So the Idaho National Laboratory, we're a Department of Energy laboratory, and we do a lot of nuclear power research primarily. We do some things also in the DoD space, but all the work that I do for the most part, everything you're going to see here at least, is in the commercial application of nuclear. And I guess the perspective you're going to see is maybe kind of unique there for given our context here. Okay, so just the basic disclaimers. I don't think that's all that important here, but what's going on? Okay, there we go. Okay, so a key piece. Actually, I should go back to the title. We didn't actually do that, did we? So I'm going to be talking about Rancor-HUNTER, so a virtual plant and operator environment for predicting human performance. And so this is Rancor is a simulator software that we developed, as well as HUNTER is a human reliability analysis software. And I don't know if people are familiar. Is anybody here familiar with human reliability analysis? Over here? Okay, yeah, I figured you probably would, yeah. Given your, we would get along quite well, I think. I like a lot of what you presented there. So, okay, well, so some of you are familiar with this. So the whole point of this is actually human reliability analysis. At least that's the, is this? Oh, it's, wait. Sorry, I don't know why it's jumping around like that. All right, so I'm just going to stick to using this. So human reliability analysis, so what is it? So it's just a structured way to identify potential, I don't like to stand there either. I'm going to try this. Can you hear me now? All right. Okay, so human reliability analysis is a structured approach used to identify human failure events and systematically estimate the probability of those events using various things. Primarily, expert judgment is really a way that we kind of started with all this, but we try to use data models more recently. And so there's a couple different types. So there's retrospective and prospective. So for retrospective, this is where essentially, we experience some kind of major event. You can think of like in aviation, you have an accident. We want to see, is this going to happen to the rest of the planes and the pilots that are flying out there? So same kind of thing that happens in nuclear. It's just a lot more, certainly hyped more, I guess, because it's, the consequences are very big, even though planes are quite prevalent in the news too. So, but anyway, that's retrospective. So we try to figure out what's likely it's going to happen again. Now, prospective is actually probably the more interesting one, though it's the one that's harder to do, and it's kind of less sought after, I guess. And that's really, we want to be able to predict and characterize the potential future events that we haven't experienced yet. Now, that one's a little more challenging because you don't have samples to draw upon there. And so, in theory, we want to be able to do that prospective one, but to be honest, we typically do it retrospectively. And a lot of the times we actually take it a step back from that, and we kind of just use it to justify our design decisions, and essentially say that, yes, our system is safe enough, given we know this. But we should be able to do it in that more prospective manner. And so, it's actually mandated in some industries. So human reliability is just straight up required for nuclear applications. And there's definitely a kind of a drive currently to, or more recently, to be able to actually apply this during the early design phase. And so right now, at least within the nuclear industry, commercial nuclear industry, we're having somewhat of a renaissance. Some people call it that, but it's essentially there's a big boom, or boon rather, in the development of advanced reactors. I should rephrase that. But there's a lot of activity happening right now, and so there's some new technologies coming in. And essentially, we're trying to scale down reactors and make more cost-effective and modular designs that are just more practical. And so to take advantage of that, though, we are going to need these new methods. Okay, and that's what this, oh, shoot, I really don't like that. Okay, that's what this next slide is going to get into. So there's kind of two recent trends. So again, I come from the world of nuclear, and the world of nuclear is very, very old. And so, a lot of the technologies, if you walk into a control room, it kind of looks like the movie Oppenheimer, if you remember that. It's very, we have analog dials and indicators all over the place. And it's very archaic. At the same time, it's very, very reliable, and it's kind of the mentality of if it's not broken, don't fix it. Let's keep on chugging along. But we're getting to the point where that's not really possible, so we're being forced to consider these things and how to update them, as well as, like I mentioned, there's this wave of new reactor technologies that are going to be able to bring power in different formats, and so we're going to have to be able to understand these new ways. And so we're having to develop these new concepts of operations. And so that includes a lot of digital technologies. and some different kind of concepts. So remote operations is a huge one, and we have a lot of projects. In fact, that's probably one of the main ones I'm working on right now. So is remote operations for some of these small reactors. Okay, and so I guess the applicability to maybe most of the folks in this room, because I don't think any of you work in commercial power applications necessarily, is that some of the methods that we've developed here either overlap or they might be applicable directly to some of the projects you're working on. Okay, so before we get too far into this, so I'm already behind. Okay, so the traditional human factor, I'm gonna get rid of this. It's not working out for me as well as I thought it would. Okay, so the traditional human reliability analysis approach. All right, it's essentially a static methodology. So what you do is you have these worksheets, and you're seeing an example of one right there. And what is this one actually for? SPAR-H. So this was developed by my mentor's mentor, I guess. But it's one of the more widely used methods in the U.S. And essentially, it provides you a method to come up with first a human failure event. So you have to kind of identify what is the human failure event that we're dealing with here. Once you've identified that, then you're able to essentially evaluate the context surrounding that, and they give you some like a glossary of terms, actually, maybe is the way you want to put it. But they give you, and we call them performance shaping factors, and associated with these performance shaping factors are quantified values. So you can either have a higher likelihood of error because of them, or you can have a lower likelihood of error. Now, where those values come from, all of them stem from one of these original methods, and that's a very, very old method, but actually it's very, very accurate, apparently. But we certainly should have better estimates with some of the advanced modeling we have these days, and that's one of the places we're trying to go with this. And so, yeah, so this idea of these performance shaping factors, and those essentially quantify the risk, the probability, as it'll change over different contexts. But then there's also these base human error probabilities. So, given any kind of thing you're doing, you have a certain base probability of failure. And so the two that are in SPAR-H here and pretty common in human reliability analysis are diagnosis and execution. And off the top of my head, I can't remember for sure. It actually might even say on this form if you can read that small. But one of them is 0.001 and the other one is 0.01 probability. So you actually, that's not as reliable as you want to be, but that's actually pretty good for the 1 in 1,000 times you do something, you make an error. Okay, so that's the traditional approach. So what's wrong with this? I think it's pretty obvious. It only works for what you know because you have to come up with the failure event. It doesn't generate it by itself. And on top of that, it's very, very labor intensive. And anytime you want to change your analysis, you have to redo it. So now there are some calculators out there. So there's one called Sapphire, and then there's another one, Kafka, I think is what it's called, which are technically PRA or larger encompassing probabilistic analysis method. But they're software that let you kind of do these things and it'll run the analysis, but it's still static. So, and by static, what I mean is it's not changing the analysis. So it's not trying to take different events and sequences and things like that, right? It's actually just looking at the whole gamut of whatever you put into it. Okay, and my boss actually put this one in. So he actually wrote the opposite of what I'm saying here, which is there's nothing wrong with these, and he's right. That's what I mentioned before. So we use these effectively today. Sure, they're good, and they've been used, but we can do better, I would argue. So, yeah, and exactly. So we can create more realistic accounts of human performance if we kind of use some of these advances in computational modeling, essentially, that other fields have already taken advantage of. It's just we've largely been ignored because nobody wants to deal with that fuzzy nature. So the number one problem you run into, in particular, if you're the only person of this kind of domain in a room full of engineers, is that, well, people can do anything, right? So, they're going to be your number one source of error in a lot of cases. And so how do you want to account for that? It's such an open-ended problem. But there are ways to systematically go about that. Or at least that's what we're trying for. So, okay, with that, we're into the dynamic. Oh, maybe I'm hitting this. That might be it. Okay, so into dynamic HRA, which is essentially, you can kind of think of it in the opposite sense. So the traditional approach is a static. You define all your inputs, and then you just calculate some kind of overall value at the end, right? Well, in dynamic HRA, you more set the constraints of what the system can do and what the human can do, and then you let the simulation run through, and then the operator respond, and then you kind of look at, when I say operator because we're talking nuclear applications here again, but you let the person respond, and you kind of see what comes out, and you can do that, iteratively by, looking at different values in different places. And you can essentially, through Monte Carlo simulation, come up with a nice range of possibilities of things that you would not have foreseen. And so in this Hunter, so we essentially, we're not the only people to come up with this, dynamic human reliability analysis method. That's not a new thing by any means. But the approach that we've used is called Hunter, which is a very mouthy, but Human Unimodel, for nuclear technology to enhance reliability, Hunter. And so there's kind of three key pieces to point out here. So there's the individual. This is essentially the person doing the task. And so the individual also represents the context that they're operating under. Okay, thanks. There's the task itself, which in nuclear, so this is one of the nice things. So nuclear, because it's, it's a fairly well understood space for the commercial operations at least, and it's highly, highly proceduralized. However, that's not as easy as it sounds, because though it is proceduralized, there's actually a lot of nuances and even the highly detailed procedures for how you can execute them. And so there's actually a lot of individual difference in how procedures are executed, but nonetheless, it's highly proceduralized, which gives us a nice roadmap for virtualizing some kind of operator. Okay, and then last you have the environment, which is really just, in our case, it's the plant model. So that's just the collection of the components, the sensors, and the actual process and how it kind of can change over time. Okay, so so there's a major problem with this. And this is a problem that PRA has not had to deal with as much because they have a much richer history of collecting data on this kind of thing. And that is, ooh, just don't touch the keyboard. Okay, we have to solve the data problem. We don't have data. And this is actually the man I was mentioning here. So this is my mentor. This is Ron Boring. So he's a very well-known, he's currently probably one of the top human reliability analysis researchers. He was actually going to be here too, but he couldn't. So at any rate, so we need to get data on people using plants, which sounds like a trivial thing because we have a lot of training. So nuclear power plant operators are one of the most trained professionals. I mean, like in aviation, you train a lot, I believe, but these people, they train, multiple times a year. So it's an immense amount of training. So just to become a nuclear power plant operator, which granted, I'm talking to a room full of people who have highly trained experts in a lot of domains, but these folks go through training after training, and the recertification that they go through is pretty intense. And so we're talking, it takes about 2 years, regardless of your background, to first know how to control one of these plants. So, and I'll show an image of it later, but a plant is about, oh gosh, I have no idea how many actual parameters. Our simulator for our plant has, or one of our plants has like 100,000 data points, right? So that's just to represent the plant. And granted, that's, multiple points within a component, all these other things. But if just think of it in terms of alarms. So there's about 800 different alarms that can go off at any one point in time, and they are related to each other. So it's actually more of like a pattern recognition kind of a thing when they do go off. But it's a very immense and complex thing. And so the challenge of that though is that it takes a lot of work to actually put together one of these studies. And so collecting the data on people interacting with this system is very challenging. Okay, so trying to tie that back together. In order to build these modeling capabilities for dynamic human reliability analysis, you essentially need a simulator to run your human study, to gather your human performance data. Then you need a similar simulator, although potentially it would be a different simulator because you want to be able to generalize. And then you can use this Hunter approach framework, software, whatever you want to call it. And you can then model the human performance. That's a separate piece that goes into Hunter, but you have to have that kind of synthesized from the human performance data itself. And from that, you can essentially create ways to replicate what we've seen empirically. And then once you do that, you can begin to kind of extend it, is the idea, right? Okay, and so, as I mentioned, so here's one of our simulators. So this is the Human System Simulation Laboratory at the Idaho National Laboratory. It essentially is representing an analog control room. So this is, I guess this is the control room. I mean, I don't know how much interest there is in actually the details of that, but you have all the different systems, and this is actually about 90% of it. You're not seeing all of it actually. But bottom line is that these are analog panels being represented virtually on touch displays that let us actually interact with them, which is a whole other interesting story about how that works, because you're trying to use some kind of physical thing that's on a virtual virtual platform, and then on top of that, you have interactions that are gestures like touch and whatnot. But anyway, it works. And so the problem is that running these studies is very, very difficult because they take a lot of complexity just planning it. So, it's anywhere from, so when you go through one of these kinds of scenarios, it can range from some of the shorter ones maybe, or 15 minutes if you're lucky, but they can go all the way up to like 4 hours, right? So, and often what happens is when we're doing this, you end up with data points of one, because it's either they succeeded or they didn't. Now, we do go into more detail about how the tasks themselves were completed within that. But it's to no point where we could actually model it based off of that. It's just we don't have enough resolution there to do that. And so it's presented a lot of problems. So over the years, the last maybe decade or so, we've actually kind of advanced some ways to collect data in this environment. And we're not the only ones that are doing this either. But it's still very challenging to get the data that we need. And there have even been efforts to actually go out to the plants themselves and collect data from them, but it's a situation where we have proprietary information as well as these are businesses, and they are regulated, so anything they report, they're a little reticent to do that because it's kind of one of those situations where you just say what you need to. You don't want to give out more information than you should. So people always said, yes, we'd love to do this, but nobody actually puts the data up when it comes time to do it, right? Okay, so one of the solutions that we've identified as a potential way to go about this is we can gather HRA data using a different platform or a simplified nuclear simulator. So this is actually my dissertation back in the day. All right, so we built the Rancor Microworld Simulator, and the idea is that because it is a simplified platform, but it actually emulates we can go into the details of what it is exactly in a minute here, which we will, but it emulates a nuclear power plant process, and so we can actually collect people doing data on that. And the idea is that we can actually collect not just operators, but we can extend that to other folks. And by doing that, we can create the capability to collect a lot more data, and granted, it's a different level of expertise, but we'll get into all that. Okay. So, so simplified reduced order model of a nuclear power plant. It's kind of a small modular reactor design. And we've done a lot of testing with this. So just to give you a sense of what it actually looks like, some of these details I don't think matter too much. But you have all the pieces of a nuclear power plant in just a simple desktop. And coincidentally, this is not something we envisioned when I was working on this back in like 2013 or 14. But this is now about the same complexity as a lot of the microreactors that are coming out. And so interestingly, there's applications like, even though it was built to be a simplified version, it actually ended up recreating what the future versions became, if that makes sense. And so inadvertently, it's maybe more applicable than ever. But bottom line is you have a series of alarms that pertain to key plant states. You have this overview display here that gives you kind of a high-level representation of what's going on with the plant. And then on the top right, that's more of your traditional view that you see in an existing control room, maybe a little more advanced than what you see now, but it's pretty close. And it's just the connections of the equipment and then some values. And then on the bottom right, you have the controls. And so you have everything you need, a complete set of controls and displays and everything to monitor what's happening to the plant. But it does come at a cost because this is a very simplified package. And so your fidelity is reduced. The scenario development is much easier. It's much more accessible. You can recruit people far more easily because the platform is easier to actually have people that can understand the scenarios. It's easier to have people that can use this from a research perspective to actually build scenarios. The drawback is that you don't have experts actually using the system, which is a major drawback. But we've done a number of validation studies to kind of try to understand that difference. And so just to give a sense of some of the applications we've used this for, a lot of my current work is actually trying to add hydrogen production capabilities to existing nuclear power plants. And on the right there, you can actually see this is one of those new systems we're trying to add. So essentially it's just using your steam you produce for a different process, but you can make a lot of money this way. And so a lot of commercial plants are looking at this. And so we didn't want to waste time essentially having operators try this out on a full scope sim. So we were able to actually kind of strap it on to our simplified simulator, have a bunch of university students, refine the HMI, deal with all the problems that we had there, and then put it into the actual full scope simulator with operators and only address then the operational issues as opposed to being kind of bogged down into, well, this doesn't make sense. I don't understand why it looks like this kind of stuff. Okay, then the other part of this is establishing, this simulator, the simplified simulator is actually generalizable. And so we've actually done a lot of work with the chosen university in South Korea. And so you can actually, these are common metrics used for these types of situations, but workload, for example, is fairly comparable across students and operators. Task time, you actually see a difference where students are taking longer, operators are more consistent. It's probably one of the key things. Situation awareness is that encompasses many different things, but you can tell that the students actually, this is one of those situations where, because it is a simplified simulator, the fact that you have simplifications means you don't have access to all the indications that you normally would. And so operators, ironically, even though they probably do have a better sense of what's going on actually, because it's overall, they should, they actually rated it as lower situation awareness because they couldn't see what they thought they needed to. Does that make sense? Counterintuitive. But, and then if you look at errors, you can see, this is a key thing here, is that these are different trials, 1, 2, 3, 4. So initially, when you use this on a naive population, right, so it's a simplified simulator used with non-nuclear experts, they perform poorly, right? That's what that error chart on the far right bottom shows you. However, you can actually bring them up to the proficiency of an operator. And so if you can do that, that's a powerful thing, because granted, you don't have all the expertise captured in here, but your mental model is getting closer, to borrow a term there. So, okay. So, transitioning. I only have 10 minutes left. Okay, cool. All right. So, so what we actually did was, how does this help HRA? I haven't actually gotten to that part of the story yet, and that's what this final piece is. Essentially, that simulator alone, right, it doesn't actually solve, well, it does solve the problem of being able to capture more data, but it doesn't solve the problem of being able to record the data at the resolution that we need to. And that's where the next piece of the puzzle comes into play, which is a computer-based procedure system. So computer-based procedures are fairly novel in nuclear. They're not well implemented anywhere. And we actually did a study where we used different levels of those and compared performance using these. And that same data actually informs HRA quite nicely, is what we found. And so they did these two scenarios, startup and loss of feed water. So startup is a routine operation. Loss of feed water is a kind of a casualty situation where you have to figure out why your feed water system came offline. So this is just an updated version of that same simulator I showed you. And on the right, though, on the right, the key thing is that you have computer-based procedures that actually guide the people walking through this scenario. So the cool thing is, without actually knowing how to control this, or maybe the bad thing too, is that you can actually walk up to this and you can actually follow these procedures and you can execute them. You might not understand why you're doing it, but you can do it. That's kind of what this is adding. Okay, so just briefly, what are, I guess, the different types of computer-based procedures? So you could think of it as a form of automation, and in fact, that's the way that a lot of these frame it. But so there's kind of two relevant standards. So IEEE 1786, which I don't know that it's a very very long title for what that actually represents, but it's a something computer-based procedures, essentially a guide. And so there's type 1, 2, and 3, and the key distinctions, which you can see in those graphics there, is that type 1 is really just a digital representation, so it doesn't actually give you live information or anything like that. Type 2 does. So you can see on that verify bypass valve position at 10%, and you can see the current value is highlighted in red and it says 0. So it just gives you intelligent indication that, or rather gives you logically coded information to tell you the state of things. Type 3 actually embeds soft controls. And so what we're moving away from is you have to now read a procedure paper-based, look at the indicators over here. You can actually do it all in one place, is kind of what this is introducing. There's another way to view it, which is more automation based, and that is it's actually, this number is actually wrong too. It's actually, it's actually 6634. I transposed that when I wrote that. But, and essentially it categorizes the different functions of a procedure. So monitoring and detection, situation assessment, response planning, and response implementation. And there I've actually just, you can see actually I've walked through the different levels that we have here. And just for sake of time, I'm going to skip over that. But the key thing, the very powerful part of this that I want to take away is because you have this computer-based procedure system, which again, some advanced reactors are looking into this, and there are the AP1000 by Westinghouse, which is not, I think there's one reactor in the US that uses that. I don't know if they actually use the digital procedure package, but it records exactly what you're doing, and the very nice thing about this is the punchline, essentially, this whole story, is that with a computer-based procedure and a simplified platform, we can now test individuals across a wide variety of scenarios, and we have explicit goals at very fine resolutions. So what I mean by that is that at any given point in time, you have a procedure you're in, and you have a procedure step you're in. That procedure step has a goal associated with it, and that larger procedure you're in has a larger goal associated with it. And so we can actually compare how you are responding to that in time and get a sense of whether or not you're doing the correct thing. And from a human reliability perspective, that's very powerful because now we have a very detailed way of recording that information. And the crazy thing is that, again, this computer-based procedures could be implemented in commercial nuclear in some cases where they have the digital instrumentation, but they won't do it because, they don't want to record data at that level. It's increased scrutiny, right? And so that's why we need these methods to come up with an alternative platform to collect these things. That's the whole thing. All right, and so one of the elusive things of human reliability analysis is this idea of dependency. So when you screw up, you make more errors, the idea. So once you start going down that path, it gets worse and worse and worse, is what we assume to be the case. But to be honest, there's not a clear picture of whether or not that's really true. And so this, the study I just showed you actually is one of the first pieces of evidence where because we're able to collect data at this fine resolution, we can actually begin to quantify that sense of dependency. So dependency can exist in a number of different ways too. There's multiple dimensions to it. So it can be like time dependency. So you have a problem here. That problem comes with you, and you might make a mistake on a different system that's unrelated. You can have inter-system related. For example, if you read the temperature wrong here, you make a decision there. It's also going to impact anywhere else. You need that temperature. Is kind of the idea. And so this has allowed us to kind of look at some of these issues. All right, and then the very final part of that is, so once we have this capability to look at how people are behaving at this resolution of detail in these nuclear process control contexts, we can start to take that model and use it outside of just human reliability analysis in general. And so that's where Hunter kind of takes off. So Hunter allows us to kind of estimate failure probabilities, but there's some other very cool applications of that. So we can actually take new procedures. So if you look at like any existing plant, they're on like Rev 189 or 256 right now. So I mean, they've been around for a long time, so they have a lot of updates. And these updates represent them refining the process of how they're controlling these things. And so what do we do though when we get to a new fleet of reactors where we don't have that historical experience to fall back on, and we have to start from anew, and we don't want to make those same errors that we presumably made to have those revisions changed, right? That's the whole point of making the updates. And so this system allows us to do that because we can actually run the simulation of a procedure. We can test what kind of error probabilities we get out of it. We can make changes to that in ways that we think would improve it, and we can run it again and see if that actually does increase or decrease, rather, the risk associated with it. And there's a key thing, too, here, which is there's actually an implicit timing associated with procedures where, because it's a physical process, right, it takes time to heat this tank. It takes time for this thing to the level to drop. The procedures are written such that, you should hit these key points at the right time. But what happens when you get off track? How do you kind of recover from those types of things? And that's where this system is really able to look at new or prospective types of situations and reveal to us problems and refinements. And that's actually kind of what this very last slide is talking about here. This is my second to last slide that's talking about. And it's this essentially operating experience review. You come up with procedures, and then you can do an evaluation, and we should have a nice set of digital procedures ready to go for our advanced fleet of reactors. That's the end of the story there. And with that, I think I'm just going to skip over this one. But thank you for your time. If you have any questions, I can answer them.
We do have time for a few questions. If you have one, I will run a mic to you.
Thank you for that talk. It was really great. So I'm interested in how you measure human error. So the way you were describing sort of the digital system which exists, it seems like in one of these plants, you made it sound like you could collect data, and because you know the procedures so well, you know what they should be doing, and if they don't do that, that's error. If you know the system, if the process is so well defined that you can define error that way, why isn't it automated? I guess is the second question.
Well, actually, so that's one of my latest proposals. I turned it in last night. But it is actually looking at generative procedures. But the problem is, they can be automated, and that's why there is a push for existing plants. I would say there's a lot of reasons why they're not, but that is actually certainly something that we could do and we probably should do. But I'm talking, I guess, more for the new. One is we don't know if our procedures cover everything until we encounter a situation where they don't, so that raises some issues, but that doesn't mean we shouldn't do it still, right? But we need to be able to, I guess, have that prospective capability to be able to foresee all those possibilities, and how do we handle that for a new reactor is kind of maybe more where I'm focused, because you're absolutely right, they could be automated. But in terms of also how do we actually measure error here, because I didn't talk about that at all, but you can actually, I mean, it's essentially kind of a signal detection theory type of approach where, you're going to have, you're going to do the correct thing. You're going to, you could actually, the problem with people too is that they can actually do the wrong thing, almost seemingly random, but that's, the case is actually, that's not it. So, and in this data, you actually see this where there was an error of commission in this situation where it turns out that there was a glitch in actually part of the software for the simulator where a button wasn't activating as it should. And so we kept seeing people recurringly try to do this action out of sequence. And it turned out the reason they were doing it out of sequence is because it wasn't, there was a glitch and it wasn't quite functioning right in some situations. But that error of commission, until you were able to look at it in this resolution, we just would have had no idea why they did that before, right? And so that's one of the, there's these different bins you can put, error of omission, and then there's actually a couple other ones too that I would mention, which is you can actually do the right thing at the wrong time. You can also do you can do it too early, you can do it too late, and so there's a lot of different ways you can define it in the end.